Good to have you back. In this outcome, we move from single variables to pairs of measurements, learning how correlation captures whether two things move together and how a regression line puts a precise, usable rule on that relationship. Up to now, we've looked at one variable at a time, but the interesting questions usually involve two. Bivariate data just means we record a pair of measurements for each item, like the hours a student revised and the mark they scored. The natural question is whether, as one goes up, the other tends to follow. Correlation measures how strongly they move together, and regression finds the straight line that best sums that up. The very first thing you do with paired data is plot a scatter graph, one dot per pair. By convention, the independent or explanatory variable, the one you control or think, drives the change, goes on the horizontal x-axis, and the dependent or response variable goes up the y-axis. The shape of that cloud of dots tells you the direction and strength of any relationship. Honestly, never calculate a single statistic before you've looked at the scatter. There are really three patterns to spot. Positive correlation is an upward drift. As x rises, y tends to rise too. Negative correlation is the downward version. As x rises, y tends to fall. And no correlation is just a shapeless scatter with no trend at all. On top of direction, there's strength, whether the points hug a line tightly or scatter loosely around it. Now, let's put words to those patterns. Positive correlation is two things climbing together, like revision hours and marks. Negative correlation is one rising as the other falls, the classic being price and quantity demanded, higher price, lower demand. Strength is about how closely the dots follow a straight line, strong, moderate, or weak. And here, we're specifically dealing with linear trends, roughly straight-line relationships. Now, the single most important warning in this whole topic. A strong correlation tells you two variables move together, but it never proves one causes the other. There might be a lurking third factor, a confounder, driving both, or it could be sheer coincidence, especially with a small sample. Only a carefully controlled study can pin down cause and effect. So always say so when you interpret a correlation. My favorite example, across a year, ice cream sales and drowning incidents rise and fall neatly together, giving a strong positive correlation. Obviously, nobody thinks buying a 99 causes someone to drown. The hidden third variable is hot weather, which pushes up both ice cream sales and the number of people swimming. In business, it's the same trap. Sales and advertising might both climb simply because it's the Christmas season. Once the scatter looks linear, we can draw a single, straight line that summarizes the trend. By eye, you'd try to balance the dots above and below it, but that's guesswork, and two people would draw it differently. So statisticians use the least squares regression line, the one unique line that makes the total squared vertical distance from all the points as small as possible. That gives everyone the same agreed line for a given data set. The regression line of y on x is written y equals a plus bx. The b is the gradient, how much y changes for every 1 unit rise in x, and a is the y-intercept, the value of y when x is 0. A useful fact is that the line always passes through the mean point, x bar, y bar. In practice, we work out b first and then use that mean point to find a. The gradient b is sxy divided by sxx. Now sxy is the sum of xy minus the quantity sum of x times sum of y all over n, and sxx is the sum of x squared minus the quantity sum of x all squared over n. The intercept a is then y bar minus b times x bar. So really you just need 4 totals from your data. the sum of x, the sum of y, the sum of x squared, and the sum of xy. The method is a tidy 4 steps. Build a table with columns for x, y, x squared, and xy, and total each one. Work out the means. X bar is the sum of x over n, and y bar is the sum of y over n. Compute sxx and sxy from those totals. Then finally, the gradient b equals sxy over sxx, and the intercept a equals y bar minus bx bar. Let's run this on 10 students' revision hours. X against their test marks. Y. We add columns for x squared and xy and total everything up. That gives the sum of x as 65, the sum of y as 589, the sum of x squared as 505, and the sum of xy as 4269. The means come straight out. X bar is 65 over 10, so 6.5 hours, and y bar is 589 over 10, so 58.9 marks. Now feed those totals in. SXX is 505 minus 65 squared over 10. That's 505 minus 422.5, giving 82.5. SXY is 4269 minus 65 times 589 over 10, so 4269 minus 3828.5, which is 440.5. The gradient B is 440.5 divided by 82.5, about 5.34. And the intercept A is 58.9 minus 5.34 times 6.5, which is 2419. So our line is y equals 24.19 plus 5.34x. Picture that line, y equals 24.19 plus 5.34x, drawn straight through the scatter. It slices through the mean point at 6.5 hours and 58.9 marks, and the dots cluster nicely close to it, confirming a strong positive correlation. The real payoff is that the line now lets us predict a mark for any number of revision hours. And because it's the least squares line, it's objective, not a wobbly hand-drawn guess. The coefficients only mean something once we translate them back into English. The gradient of 5.34 says each extra hour of revision is associated with about 5.3 more marks. The intercept of 24.19 predicts roughly 24 marks for a student who does no revision at all, though treat that as a rough guide, since zero revision may sit outside our actual data. And that positive gradient simply confirms the upward trend we already saw on the scatter. Let's actually use it. Predict the mark for a student revising 8 hours using y equals 24.19 plus 5.34x. Substitute x equals 8, that's 24.19 plus 5.34 times 8, which is 24.19 plus 42.72, giving 66.9, so about 67 marks. Now, 8 hours sits inside our data range of 2 to 11 hours, so that's interpolation and reasonably safe. Predicting for 40 hours would be extrapolation, way outside the data and not to be trusted. This is worth dwelling on. Interpolation means predicting inside the range of X values you actually collected, and if the correlation's strong, it's generally reliable, like our 8 hours estimate. Extrapolation means reaching beyond that range, and it's risky because the trend simply may not continue, like assuming 40 hours of revision keeps piling on marks. The line knows nothing about the world outside the data it was built from. One subtlety worth flagging. The line of y on x minimizes the vertical distances, treating y as the thing we're predicting from x, so it's designed to estimate y for a given x, not the other way round. Which variable you make x and which you make y depends entirely on what you want to predict. Here we're predicting marks from revision hours, so hours is the explanatory variable on the x-axis. Let's keep the symbols straight. The gradient b at 534 is the marks gained per extra revision hour. The intercept a at 2419 is the predicted mark for zero revision. The y in the equation is the predicted value, our estimated mark for a chosen x. And the mean point, x bar, y bar, is the anchor the line must always pass through. A regression line is powerful, but it has real limits. It only fits a straight line trend. So a curved relationship needs a different model entirely. It's sensitive to outliers, which can tilt the whole line. And awkwardly, you can fit a line even to completely unrelated data. So always check the scatter and correlation first. Extrapolating beyond the data can mislead badly. And remember, a fitted line still doesn't prove causation. Here's where it earns its keep. Say a retailer like Tesco logs weekly advertising spend, X, against sales revenue, Y, and the scatter shows a clear positive linear trend. Suppose the fitted line comes out as sales equals 120 plus 4.5 times spend in thousands of pounds. That gradient of 4.5 suggests every extra £1,000 of advertising is linked to about £4,500 more sales, which managers use to plan budgets, though they'd be wise not to extrapolate wildly and to remember that season, price and competitors all matter too. So, to recap, a scatter graph shows the direction and strength of a linear relationship. Correlation measures association only, never proof of cause, so keep an eye out for confounding variables. The least squares line of y on x is y equals a plus bx and always runs through the mean point, with b equal to sxy over sxx and a equal to y bar minus bx bar. Use it to interpolate safely inside your data, but be wary of extrapolating beyond it. That brings our look at correlation and regression to a close. To take it further, Rowntree's Statistics Without Tears is a gentle way in, while Crawshaw and Chambers gives you the fuller mathematical treatment of the least squares line. The Royal Statistical Society's Significance magazine has genuinely readable pieces on correlation and its pitfalls, and the Office for National Statistics site is a goldmine of real bivariate data. Corbett Maths and BBC Bitesize are there if you want more worked practice, and remember, it's all linked on the Moodle for this unit.